Okay, it's a great pleasure for me to introduce Mike Norton, who is kicking off our new season or new semester of SLAAM seminars. I've known Mike for a few years, but should have known him even a few years before that because we were both getting PhDs at University of Pennsylvania at around the same time. But he was in the Department of Mechanical Engineering, where he got his PhD with Haim Bao. He got his undergraduate degree in mechanical engineering at Rochester Institute of Technology, which is also where he works now, following postdoctoral positions at Brandeis University and at Penn State. And it was at Brandeis that he got into this work on active nematics and on oscillator networks, these Belousov-Zhabotinsky reactions. And that's where I learned about his work. And it's really beautiful stuff. And in recent years, Mike has moved into machine learning and optimal control theory, which is something more from the dynamical systems world, and really bringing a fresh perspective into the world of soft matter and active matter. So it's great to have him here as our speaker. And Mike, I'm looking forward to your talk.
Excellent. Dan, that was a great introduction. Thank you so much. And thank you and Niranjan and Kinjal, who's not here, for organizing this. So, I mean, Dan totally took my first slide, so I don't need to say any of this. But basically, I'll just say that the work that I'm going to be talking about today is work that I started at Brandeis University with Seth Radin and Mike Hagan on oscillator networks and active nematics, and sort of continues on now through a collaboration with Piyush Grover and Jason Park. We have a Department of Energy grant together. And work that I won't be talking about today, but is sort of ongoing, is my work with Moumita at RIT, where we're trying to apply some continuum modeling techniques to the pattern formation in bacterial chromatin or DNA protein condensates. Okay, so this is probably sort of, this viewpoint is sort of familiar to you guys. You know, like you, I like looking at biology through the lens of physics, but I think I'm also interested in bringing a dynamical systems view to biology and these kind of dynamical materials that are arising on the physics end. And so I guess, no, sorry, I'm just trying to get my Zoom out of the way here. And so I think the reason why we're sort of interested in these extremes, right, is that reconstituted systems or model active systems have a lot that they can teach us about the really complex dynamics of fully living materials, such as this Drosophila embryo that you're looking at here. But sort of the other end of it that sort of philosophical view that I was exposed to while I was at Brandeis is also, you know, looking at biological systems as inspiration for what is possible in terms of building completely synthetic active materials, right? And so there's this nice interchange of ideas between biology, material science, and physics that I think is really interesting, and I think has captivated, you know, all of our imaginations. To maybe make that a little bit more specific, right, on the synthetic and reconstituted ends, like why do we like these systems? It's because we have, you know, controlled composition. We have control over their compositions. There's minimal constituents, right? On the other hand, right, they have limited functionality. Living systems, by contrast, very complex compositions. Their dynamics have function. And what's, I think, the most important thing to me in the way that I've been sort of looking at these systems recently is thinking about them in terms of the degree of regulation, right? Living systems are highly regulated. Their spatiotemporal patterns are controlled by, you know, very complex protein and genetic networks, right? Whereas the kind of materials that we're building in the lab are, you know, for lack of a better word, are sort of like blank slates. They're relatively unregulated. And so I think this is an opportunity to, you know, take ideas from dynamical systems and control theory and ask a few interesting questions. For the synthetic systems, we can ask, what kinds of external inputs need to be applied to these systems in order to make them execute specific dynamics, right? So we'll be looking at the microtubule suspension and networks of Golubov-Zeputinsky reactors in a bit here, but what else can we get out of these systems by poking at them in strategic ways, right? And then what I'll close with today is sort of a look at how control theory might come to bear on living systems. Can we develop new ways of culturing tissues, new kinds of therapies by formally applying control theory to living systems? And so that's sort of the trajectory for today's talk. I'll start with synthetic systems and then close with a few just thoughts on living systems. And I guess I should say before I get fully into this, if there are any questions that show up, I can't see you guys raising your hands or anything, but I would say, Dan, if there's any questions, to just interrupt me and I can try to field them as we go. So the first system I'm going to look at today is one that's familiar, I think, to a lot of you. This is what you're looking at here is a dense mat of microtubules that are floating on an oil-water interface. And they're made animate by these kinesin motor protein complexes, right? So these motor protein complexes are grabbing on to multiple microtubules at a time, and they're shearing them against each other as they process along the microtubules. And the net result is a system that is naturally extensile. And so what you're looking at on the left here is just the normal sort of chaotic motion. If we zoom in on a patch of locally aligned microtubules and do a photo bleaching experiment, this was done by Linnea Lemma, we can see that extensional motion like really brought to the fore here. This patch that started off square is slowly becoming elongated in the direction of the microtubules. So we see that we're extending along the local orientation of the microtubules and contracting in the other direction. And so, why is this system look the way it does? One way we can understand that is by looking at sort of the initial onset of instability in this system. So if you were to flow align this system, as was done in the lab of Guillaume Duclos at Brandeis, we see that the moment that the flow is removed, a characteristic wavelength in the bending of the microtubules appears that grows over time. And what's happening here is there's some undulation, and that undulation is creating an active flow, which further exaggerates that undulation. And eventually these bends and folds saturate into these topological defects that chaotically interact with each other. So we can sort of quantify what we're looking at a little bit more precisely here by finding the director field for this system and actually locating the topological disclinations in this director field. I'm not going to be talking too much about the specific dynamics of defects today, but there's been a lot of work done on quantifying the dynamics of active nematics through the statistics of these defects. What I'll say now is just that these two different kinds of defects have associated with them qualitatively different kinds of active flows that propel them. And so in the case of the plus half defect, it's this comet-shaped object, right, that I'm labeling with a pink arrow here. It tends to act like a self-propelled particle. In contrast, the minus half defect, while it does create active flows, because of the symmetry, they don't tend to propel themselves. So one of the grand challenges in this field from the sort of design point of view is how to control the dynamics of these defects, how to control the structure of the director field in these materials. And I'm just going to highlight a few of the efforts that have been going on over the past half decade or more. In the case of these left two, the oil layer that the microtubule mat is floating on has been replaced by an anisotropic liquid crystal. And so now we've broken the symmetry of this underlying layer, and we've given preference to certain kinds of motion of the microtubules. In the case of this far left movie here out of Francesc Sagas's group in Barcelona, the easy way for the microtubules to move is north and south, and so you end up creating these lanes. In this middle pane here, the underlying liquid crystal layer is forming a focal conic domains, and so there's these circular domains of varying size, and the size of those domains, that you can't see them directly, is influencing the microtubule motion, and so you end up with this this sort of like lattice, this disorganized lattice of vortices that is persistent over time. Even though there's some transient dynamics, on average, these vortices remain over these focal conic domains. And then finally, this is work that I collaborated with Achini on at Brandeis. And here she's loading the microtubule suspension into microfluidic wells. And so we have a hard wall boundaries sort of corralling the nematic and causing circulation. So a recent advance that's really interesting to me is that this is a collaboration between Zonyamir's group and Matt Thompson's group. They've taken those motor protein clusters, and instead of having them be permanently bound to this biotin streptavidin connection, have been functionalized so that they are they only dimerize in the presence of light. And so now there's this possibility of creating spatial temporal control for this system. What you're seeing here is a circular, in the circular domain is where light is being applied. And so that extensile buckling stress, right, it's only being generated in that small region. You can see that far from that region, the nematic is, while it's being influenced through the fluid flow, is not active. It's not actively extending. This is an example of that in work. It's a different kind of light activation, but the net result is the same. This is work from Juan de Pablo and Margaret Gardell's group. And here they're shining this elbow-shaped pattern onto an active nematic. And they find that they can basically, cause the plus half defects, the comet-shaped objects that I highlighted earlier, will sort of follow this track. Right. Another input that that's some folks at Johns Hopkins are looking at is the application of a spinning disk to the active nematic. And so here there's a magnetically actuated rotor that's floating above the active nematic layer, and by manipulating the magnetic field, they can spin up this disk and create flows in the active nematic. And so, taken together, what we have here is this this whole suite of different ways that we can interact with active nematics to shape their dynamics. Right, particularly the rotor and the optogenetic system, right? Both of these have the potential to apply, complex spatial temporal inputs into the active nematic to shape it into new configurations. And the question that drives me is asking, well, if we have this ability to apply these inputs, how do we do so in a systematic way to arrive at specific configurations? Right, so everything we've looked at so far is kind of ad hoc, right? We're applying an elbow-shaped lane to the system and seeing what happens. But now, what if we try to go the other way and say, I have some complex, lattice of vortices I want to create, or some other, non-trivial pattern. How do we go back the other way to find what those inputs need to be? Right? And so if we're going to do that, we're going to apply control theory. And the first thing we need to do is have a model in order to apply control theory to it. And for that, I'm going to We need, governing equations for the director field. For that, I'm going to use what is essentially the standard model for active nematics. So this is a Landau-Dijen kind of model for a liquid crystalline fluid. And the main difference is that we have momentum injection coming from this active dipolar stress field, right? So we're in the overdamped Stokes limit. We have that plus Landau-Dijen, and that gets us our dynamical equations plus boundary conditions. So, before we apply control to this thing, what do these governing equations do if you just throw them into a disk? There's a characteristic length scale that governs active nematics that goes as the square root of the Frank constant to the active stress strength. And this roughly sets the wavelength of the bend instability and the average spacing of the topological defects. And so if you make a domain that's much larger than this active length scale, then what you end up with is this chaotic motion that we were seeing in the experiments, right? Where defects are, constantly nucleating, swimming around, mixing the fluid, annihilating, and so forth. If we shrink the domain size to be, more commensurate with that active length scale, what we get is something a little more regular. In fact, we get a fully stable attractor state for the system that consists of 2 +½ defects that just perpetually rotate around the system. Okay, and so again, I've labeled the defects as magenta arrows. And one thing to note about this is that even though this is sort of the topological minimum of the system in some sense, right? That we have 2 +½ defects. We don't have any extra -½ +½ pairs showing up in the system. This sort of wound configuration of the director field is not something you would see in an equilibrium liquid crystal, right? So this is sort of unique to the active nematic.
I have a quick question on this, Mike.
Yeah.
Are you setting flow boundary conditions, anchoring conditions, or both?
Yeah, both in this case. So yeah, parallel anchoring and no slip and no outflow. Yeah.
Okay.
Yeah, thank you.
Thanks.
Can I ask a quick question as well?
Yeah.
So do you know anything about the uniqueness of this attractor state? If you started from a slightly different or much different initial condition, would there be qualitatively different attractors?
That's a great question. I know I'll touch on that a little bit more later for other geometries. For this particular activity value, this was the only attractor that we found. So there's this attractor, and then there's the mirror image of it. That appear to be the only stable attractors. And I'll say about that's actually going to be the purpose of the control. It's going to be flipping between these 2 attractor states.
Okay, thanks.
There's also a question from Robin Sellinger in the chat. Does the model conserve angular momentum?
That's a great question. I believe it does. But Robin, was there a feature of the model that piqued your interest?
If I'm allowed to unmute, I'll just ask. I mean, I'm trying to do agent-based models of this system. And so the question is, if the system's going to flip velocities from going clockwise to counterclockwise, it needs attraction force. And that has to come from the boundary. And I was just wondering if that's in your beautiful continuum model. Thanks. I'll unmute, or I'll remute.
That's a great question. And I don't have, especially when control is being applied, we seem to be able to do it without attraction force in the model. But I see what you're saying. That it feels like we're cheating somehow. Maybe we can talk about that more at the end, but that's a great question. So I guess as both of those great questions alluded to, right? In order to do this control problem, we need to have a control goal of some sorts. And while we could choose to steer this system to any arbitrary configuration, I thought as a first step of just getting our feet wet with control theory applied to the system, that we would sort of work with the native dynamics of the system by just flipping it from one attractor to the other. And so this is sort of just a schematic in phase space. We have a clockwise and counterclockwise attractor, and our goal is to find the control input that creates a trajectory that moves us from one direction of precession to the other. And our control input is going to be varying the active stress strength. So this is mimicking essentially the optogenetic problem. Okay, and so we need a few ingredients in the way that one usually constructs these optimal control problems is to try to minimize some cost or penalty functional of the system. And there's a few pieces to it. The first is obviously we have a state penalty. We want to penalize the system for not having the dynamics that we want it to have. We're also going to penalize how much we change the activity in the system. So in order to support these two attractor states, we need some amount of activity, right? So we want to, and that's going to be our alpha naught here. And we want to sort of minimize the deviation away from that required amount of activity. And to just keep the numerics well behaved, I'm also going to penalize the gradient in the activity. Okay. And so the next bit of this is that we want to minimize that functional, but we want to do it in a way that respects the dynamics of the system. And for that, we're going to augment our cost function with this constraint where it's essentially a PDE constraint where the F sub U and F sub Q here are the dynamics that I showed from our model. And in addition to our paper, there's also a recent paper that came out that applies the same formalism to a slightly different problem in active matter. And since we're trying to optimize this thing, we're going to either maximize or minimize this quantity by taking variations with respect to all of our state variables and our adjoint variables or co-state variables that I've introduced here. And this ends up producing, I'm showing it just to illustrate the fact that when you do this, what you end up with is a system of PDEs for your adjoint variables. And they get pretty hairy, but one part about them that I think is interesting and sort of lends some intuition to this whole process is that your adjoint equations are in some sense driven by the state residual, right? So this came directly out of our cost function. And so you can think of our adjoint variables essentially adding up the errors in our state, right? So how far we are from where we want to be. And then finally, we also have some optimality conditions on the control field itself. This is all can be solved numerically using a process called direct adjoint looping. It's essentially glorified gradient descent, but it's most commonly used in the fluid dynamics literature to solve these high dimensional optimization problems. Okay, so now we're going to actually see what the solution looks like for our system. We're going to track the director field in time, the active stress field, and the flow field. And so this is this middle one being our control input. And so the time and space evolution of the control field, I think, is rather complicated, but there's a few things I can point out to kind of guide our intuition here. I think the most important one being that, in order to go from one-handedness to another-handedness, we have to pass through this point of symmetry, right? And so we do see that the director field is, roughly configured in this sort of dipolar configuration around time equals 0.96. And what's interesting here is that when you look at the active stress field that's being applied at that moment, that it has a handedness, right? And so one way we can make sense of this control is that it's bringing us to this point of symmetry and then sort of pushing us over the hill, right, with the right handedness. You can sort of imagine that if you were at this point, but you had mirrored this control signal in, that you would end up back in the other attractor. And we can also plot some sort of global metrics of the system to just sort of track where we are in time. And so you can, one important one is the circulation. So this is just the total amount of flow that's in the tangential direction here. And we sort of see, around actually slightly before this point of symmetry that the flow has started to go the other way. And here I'm just going to show a movie of that series of images. I'll actually pause it here and go back to the beginning. So we're going to start a little bit before the control input actually starts. So when t equals 0, the director field is going to light up blue. That's when the control input is actually started. This is our reference solution. And the thing to note about this is that this is always moving. So we're doing what's called a tracking problem, where our target is also evolving in time. All right. And, so I guess I'll be, the first to admit that the active stress field that we found, while one can sort of pick it apart and make sense of it, I think is not totally intuitive. It's not the pattern that I would have drawn, on the back of an envelope to try to do this control problem. That was, in fact, part of the purpose of this whole exercise, was to try to find, what that shape is. To sort of check our process, I did another control problem where instead of manipulating the active stress field, I manipulated the vorticity of the flow field directly. And so in this case, I just augmented the vorticity tensor with this tensor G, defined as follows. And so now that is our control input, and this is intended to sort of mimic the action of a rotor floating above the Nematic. Obviously, I'm not simulating the full fluid flow. This is just sort of an approximation of that dynamic. And so we're going to do the same process with a very similar kind of cost function. And we indeed get an answer that has some spatial complexity, but I think is more intuitive in the sense that the vorticity that we're applying to the system, has the opposite sign of the vorticity of where we're starting out, right? So it's intended to just override what the system is trying to do at the beginning. And once you again get over that that hump of symmetry, then the control decreases substantially, and you wind up in the attractor that we're shooting for. Let's see how we're doing on time. Okay.
So Mike, is this spatially and temporally uniform, the vorticity you're applying now?
No. So yeah, in this case, we're still seeking we're still seeking something that's allowed to vary in space and time. We could have done it the other way too, and just sought a time series where it's spatially uniform. That's totally doable in the framework. But again, our goal was sort of two-purpose. One was to find the solution. The other was to also sort of make sure that the adjoint dynamics were behaving properly.
Yeah, I mean, one question that came to my mind on the last couple of slides is how much can your framework say how much worse it would be to just do something spatially uniform but time controlled?
Yeah, that's a great comparison. And certainly, yeah, you can do that. You can do the control problem where it's spatially uniform. In fact, you know, the initial guess that I applied for this system was basically a step function where it was a uniform vorticity up until some time, and then it turned off. And because I knew that would do the job, right? But yeah, you can certainly compare that to the time it would take to do it with this optimal one and see, yeah, do you really gain anything by having the spatial specificity, or how much do you gain? That's definitely a question you could answer.
Thanks.
So another way that I like to think about this system, right? It's a little bit unwieldy because it's this high dimensional PDE. But here I'm just sketching out, this is not a formal reduced order model or anything like that, but you know, one can sketch out a three-dimensional system that has some of the same features, right? It has two limit cycles that are rotating in opposite directions, and sort of in between those two limit cycles in phase space is this continuous ring of stationary states, right? And the reason why I'm showing you this cartoon system, right, is to point out the fact that here it's like really obvious that if you're going to do control on this system, it's got to be, your input has to be in the Z direction, or at least there has to be a component of the control that's in the Z direction, right? Because there's no dynamics otherwise that are going to carry you from one attractor to the other. In our active pneumatic system, it's totally unclear what the Z direction is, right? And so in some sense, the optimal control has helped us identify the correct direction to head in phase space. And so that's part of the power of optimal control and these adjoint techniques.
Michael, may I interject?
Yeah.
I'm John Texter, and the previous questions raised some issues that I think in the older control literature are referred to as controllability issues. And so the merit of developing understanding of what it might take at each point in space as a forcing function or control application versus controlling boundary conditions or some intensive field condition that say may know how to affect, I think is a significant issue. So, or maybe this is being taken care of in your study, but I'm asking, you know, is the control you're seeking something that you can readily implement? Is my first question. Second is, in talking about switching from one attractor to another, this really gets into nonlinear necessary and sufficient conditions as another approach to determining switching.
Yeah, no, this is a great question. So I've done a little bit of controllability work for linear and nonlinear systems, but it's always been for ODEs. And to be honest, I'm not really sure how to go about the formal controllability problem for the full PDE system.
Maybe we could talk offline. I published a paper on the necessary and sufficient asymptotic stability of competing bistable systems back in the 80s with a Dirichlet type of spatial and temporal system. But let me contact you offline about that.
Yeah, that'd be great. So you're talking about a boundary control problem, or your boundary actuated problem.
Well, so and it well, the solution was cast in what kind of let's say what frequency components and an inhomogeneous perturbation would need to have, and their magnitude, in order to switch from one attractor to another.
Gotcha. Okay. Yeah, that'd be great. Let's definitely
I'll call you later.
afterwards. Okay, great. Thanks a lot. Okay, so this was I alluded to this a little bit earlier as well, but one direction that we want to go with this is to look at control in other geometries. And this is a movie that you may have seen similar versions of. This was work that was originally done by Tyler Shendrick with Julia Yeomans. And so there's this, when you put the active nematic into a periodic channel, you get this dancing disclination state, right? What we found is that actually in addition to this one periodic solution, there's actually a whole host of periodic and quasi-periodic solutions that show up in the phase space of this problem. So this is computational work that's being done by Caleb Wagner, who's a postdoc with my collaborator, Piyush Grover. And so he's really painstakingly gone through and explored the phase space of the system. And so it's a lot more complicated than the situation that I've showed you so far. And what's interesting about it is that there's attractors, but a lot of these coherent flows that I was showing on the previous slide are they're high dimensional saddle points, right? So they have some attracting directions and then a few repelling directions. And control in this context gets really interesting. You can start thinking about sort of using the native dynamics of the system to get to some point in phase space, and then just nudging off of that saddle point to get someplace else. And this movie is way too long to play through right now, so I'm going to kind of like skip through it. But I really encourage you guys to check it out if you're curious about it. So what we're looking at here is on the left here, sort of like a reduced phase space for the system with some channel average quantities here. On the right are the nematic order fields and the vorticity. And he started off in a uniform laminar state. It's unstable, so he pokes it in some direction. And then it has this very complicated path and phase space that sort of visits these other high dimensional saddle point states, right? So they tend to, the system trajectory will reside near them for some amount of time and then get kicked off and go someplace else. And so the idea here is that even though what's happening, on the right can look quite chaotic over time, actually you can sort of understand these quasi-turbulent dynamics through this phase space lens. And if there's more questions about that, maybe we can field it at the end. So I want to change gears a little bit, and I see I'll probably have to go through this a little bit quickly, but I just wanted to share the other application of control theory. And we're going to look at a system that, even though it's entirely different, the example I'm going to show is almost identical to the one that we just went over. And so what you're looking at here is the Belousov-Zhabotinsky reaction. And we're in a Petri dish here. The time scale for the oscillation is about 300 seconds. And the color change here you're seeing is giving you a sense of the period or the phase of the oscillation here. So we're going from an oxidized blue state to a reduced red state. And you can sort of I guess the way that I sort of think about these oscillators is that we have a light switch that can turn itself on or off. If we start at the oxidized state of the system here, it's producing, as this catalyst is oxidized, it's producing an inhibitor that's eventually going to shut off that oxidation. But that inhibitor that's produced takes a long time to get chewed up by the other chemical processes of the system. And once it does, then the catalyst is able to oxidize again. But of course, the system, it's not a perpetual motion machine. The process of oxidizing and reducing this, the catalyst consumes some chemical fuel in the form of malonic acid. And so you can think of this system as having a very sort of simple metabolism, right? That's allowing it to undergo these color changes. And this is the sort of the classic oreganator model. It's a 3-component model that captures the relaxational dynamics of the system. Okay, and so if we take that same BZ mix, but now confine it to PDMS wells. This was work that was done by Thomas Litchell at Brandeis University. So he's confined the system to very small microfluidic wells where we sort of have this sandwich between PDMS and glass, and we're shining bluish light through the system. And so anytime the catalyst changes color from red to blue, we register it as a bright flash here. But the difference between these two lattices is that one of them has little fluidic connections between the adjoining wells, and the other doesn't. It just has PDMS boundaries, right? What's interesting is that if you're watching the video of this, it doesn't seem like there's any sort of coherent pattern being formed. But if you look at a space-time plot of just one slice of this system, so you take all the pixels from this line and you play their value over all the frames of the movie, you see something, quite a bit of structure happening. In fact, we see that these oscillators are oscillating nearly perfectly antiphase with one another. And that's because these oscillators are only exchanging the inhibitor species of the BZ reaction. And so they're trying to basically repel each other on the clock, right? And so we have these two very different kinds of patterns forming. One that tends to, one material tends to permit waves, while the other one is going towards this antiphase kind of synchrony. And so if you take that same inhibitor coupled system and confine it to a ring of just 3 wells, again, we see the emergence of these two I guess that's great. Are you guys all still there?
Yep, we're here.
Yeah, we're here. We're
Okay.
seeing your Microsoft error.
All right. Sorry about that. It'll take me just a moment. I just like updated my operating system, and I knew I was gonna get bit at some point. I guess while that's loading, when do questions start? Do we start at the end, or do we leave a few minutes?
So for talks like this, where we've had plenty of good questions along the way, if you're happy to continue fielding questions on the way, we can go up until the hour.
Okay, great. Yeah, I'll go through this relatively quickly. Let's see. Okay, and so what makes the BZ system great is that we also have this, optogenetic like ability to manipulate the phase of these oscillators. Okay, so if we shine light on them, low amounts of light will elongate the period of oscillation, and then high amounts will stop it altogether. And so we basically have a problem that's very analogous to the active nematic system, but it's much lower dimensional, right? Because we just have these sort of the phase of the oscillators to worry about. And so we can talk about this more if there's interest in it, but the sort of the lowest order model that you can create for this system is called the Kuramoto model, and it has this nonlinear coupling function that goes as the sine of the phase difference between neighboring oscillators. And so you can add all these up to create a small system. And in fact, it turns out that all of the right-hand side of this equation, when you write them out for each of the oscillators in this ring of 3 that we were looking at, only the phase differences matter. And so we can reduce the system from 3 degrees of freedom down to 2 and plot the full phase space for this system, which is great from a visualization point of view and for building some intuition for this system. The 2 wave states that we're looking at are the 2 states circled here, and you can see that the system is flowing towards either clockwise or counterclockwise, depending on where you start off. So, using the natural frequency of the oscillators as our control input, because we have this optogenetic control over them, we can see how the phase space gets manipulated as we dial up and down the light. And so what we're going to do here is look at a particular pattern of light where the frequency differences between 2 and 1 and 3 and 2 are equal to some constant, and we're going to vary that constant. And we can see that at different values of that alpha value, we cause different bifurcations to take place in the system. And what turns out to be really fascinating is that at some critical value, right, you actually remove one of the attractors from the system entirely, right? And so even really without optimal control, we can see that we're going to be able to control this system to get it to flip from one chirality to the other. But nonetheless, we can still apply optimal control to figure out, exactly what's the minimum amount of light that needs to be applied to this system to get it to do that transition. And that's meaningful because, light really messes with the chemistry of the system. So it makes sense from an experimental point of view to try to minimize the perturbations on the system. And so this was work that was done by Chris Simonetti, who was a really talented dual major math and physics major at Brandeis. And so here's the system without control. And so you can see that basically the control brought the system to the point where that first attractor in red had been eliminated, and then closes up the system behind it once it's close enough to the desired attractor. Okay. And so, the takeaway is this. I think, optimal control is providing like a really powerful way to, probe these multi-stable systems. Because these systems in both of these cases are, they're athermal in some sense, right? They're not going to naturally probe all of phase space by themselves, right? Unless there's like a lot of noise in the system for some reason. So if you really want to explore these systems, you need some way of strategically coming up with spatial temporal inputs. In the case of the oscillator network, it was sort of intuitive what that pattern should be, but for the active nematic, it was less easy to spot. And so now I guess just to conclude, I just want to share sort of like what I envision is, sort of my dream for this kind of system is to actually set up model predictive control loops where we're running models in tandem with experiments, right? And the reason why you would need to, couple the control to the microscope is because, it's very unlikely that, the model is going to be totally correct. There's always going to be some amount of perturbations to the system that aren't captured. And so one would need to like rerun the control repetitively to actually steer the system towards some desired configuration. And to look even sort of further ahead, I like thinking about the idea of bringing these same model-based tools to look at actually like living systems that have been optogenetically modified, and steer things like tissue flows during morphogenesis. And that may seem like a big jump in going from these model systems to these fully living systems, but there's been so much work done in the past decade or so, both on the experimental end and the modeling end, that I think this is, at least it's not so crazy to think that we can do this. And I'm just going to point out a few examples that have come out recently. So this is from Noah Mitchell's work looking at organ morphogenesis. He gave a great presentation a week or so ago at the Boulder Physics Seminar Series. The other one I want to highlight is Boris Freeman's work, where they were able to, using light sheet microscopy, measure the actomyosin network in a Drosophila embryo and actually predict the morphogenic flows that result from that network using a really simple model. And I'm just showing it here. We can dig into it more later if there's questions. But the point is that this model is like not so different than the active nematic equations that I was using. It's not really more complex, right? And so I think it's reasonable to start asking, right, if one can start to manipulate the actomyosin network and its activity with optogenetics, can we start to shape the tissue, the flows of cells in these embryos and other things? And so with that, I want to conclude and just thank all my collaborators and the students, postdocs that have helped me do this work, and open it up to any questions.
Okay, let's all give our speaker a virtual round of applause. A wonderful talk. And we have a couple of questions already queued up of people who were patient in the last few minutes. So Sayed Rojin, I'm sorry for probably mispronouncing your name, but could you unmute and ask your question, please?
Hi, can you hear me?
Yes.
Okay, so I wanted to ask, when you mentioned the pre-turbulence, so is that like, do you aim for seeing turbulence, or is that like, is it different from transition into turbulence, or you're really aiming for seeing the turbulence, whether or you're just seeing through time, your system will evolve turbulence behavior? And if yes, to either of these questions, then how does the pre-turbulent time scale to the turbulent time? So it means that if you want to see turbulence behavior, do you set your pre-turbulence as an initial condition, like to introduce it to your computational model? And so if you explain about that, that would be helpful.
Yeah, thanks for the question. It's actually, that's a great question, because yeah, so the reason why I use the word pre-turbulent is because in the long time, the system does settle down to one of the few attractors that it has. So I think I can't remember exactly what the number is, but I think there's like 3 or 4 actual attractors of the system. And so in that sense, it is not like turbulence. But when you go to the idea here, and this is something that Caleb and Piyush are looking at now, is that when you ramp up the activity, you're going to destroy all of the attractors, and all you will have left is this meandering path around the sort of skeleton of all of these partially stable coherent attractor coherent states. right? So I hope that clarifies. And yeah, I think the details are in that paper as well.
Okay, thanks.
Thank you.
And Fareshta had the next question.
Hello. Thank you for the great talk. I was wondering if we have multi-layer 2D active nematic. Eventually, after some time, will they move with the same frequency and velocity, and they become kind of like a one single quasi 2D layer, or they will just keep moving separately?
That's an interesting question. So you're envisioning, like, if you were able to do like a oil, water, oil system and then put multiple microtubule layers, and then asking like whether they would sort of like synchronize to each other over time.
Yes.
I mean, that seems like a question for the experimentalists. I mean, I would imagine that if they were close enough to each other, if you could create such a thing, that the hydrodynamic coupling would lead to synchronization between them. But
Oh,
I don't know. I've never really thought of it. That's interesting.
thank you.
Thank you.
It's this question is just inspired by that paper. I don't remember the author, but that paper that they had some liquid crystal and active nematic, and active nematic was had a similar pattern and vortices and lines as we were changing the liquid crystal on top. Thank you.
Yeah, that makes, I see. Yeah, right. Yeah, I'm just wondering if one would be able to actually make such a system. Is because I think one of the steps that they use to make the 2D layers, that they have to centrifuge things down to get a dense enough layer, and so that would probably destroy the 2-layer system that you're trying to make. But I think it's an interesting, at least theoretical question. Yeah.
Thanks.
All right, other questions?
Yeah, thanks for the nice talk. At one point you mentioned this optimal control gives you a way to probe multi-stable systems. I'm not too familiar with this optimal control stuff. Can you elaborate on that? Like, do you mean like to identify or chart out the different attractors for some large dynamical system? Like, what do you mean?
Yeah, no, thanks for asking me that. Yeah, what I had in mind, and I didn't give a very good example of this, but for example, I guess I'll give like another oscillator network example. So when you put this BZ network into a 4-ring network instead, you end up again with a lot of competing attractors, but they have like really different, the size of the bases of attraction are really different. And so what that means is, if you were starting from like a random distribution of initial conditions, it would be very, very hard to actually end up in all of these states. And so if you were of the mindset that you wanted to like really prove that your theory was correct, that there really were these other attractor states, then you're going to need some way of steering the system towards these like more rare configurations, right? Rare just meaning the fraction of the phase space that is the basis of attraction for that particular attractor, right?
What I'm confused about with that is like it's almost like you need to know the attractor is there in order to search for it. Like you have to target that region of phase space in order to then go see that it's an attractor, right?
Yeah,
you see what I mean?
Yeah, I mean 100%. Like, yeah, I mean that's it's sort of it's a little bit circular, right? But
yeah, I'm just wondering if there's like a free lunch thing going on. Because this would then have implications, of course, for like optimization and like machine learning and all that, if you could go find like these deep minima and all that, right?
No, yeah, no, it's nothing like that. I think all I'm meaning is that, like, you know, you have a theory, it predicts that certain things should be there in phase space, but maybe you don't see them experimentally. And this is something that we found that actually we were confronted with, is that there were just some things that were so rare that, you know, we weren't getting there naturally, right?
Mm-hmm.
And so optimal control could be this way of like validating theories in some. It's a little bit maybe a long walk, but that's what I had in mind.
Okay, thanks.
Yeah, thanks for your question.
Michael, if I
Yeah.
may, and please forgive if this sounds polemical, but I'm if you just I'm kind of an old engineer, and so I think these very interesting concepts, some of which are nonlinear, some of which are linear, are being associated with a mixing of the concepts of optimal control and let's say the qualitative theory of nonlinear partial differential equations, which would address the existence of critical points, their local and asymptotic stability, and attractors, their local and asymptotic stability on the one hand, which a lot of this discussion is aimed at, versus control theory, which I think really embraces how do you force something dynamically or statically to move in some desired way. So the control theory typically, traditionally, requires a functional as you've displayed, and you going back, I haven't heard Pontryagin's name in quite a few years, but you know, and we have to thank the Russians for giving us this engineering tool. But whenever you say optimal control, you have to define what you mean by optimal. So that basically means show us a functional or something that you're variationally trying to minimize. And so this is not unique. It depends on the person trying to manipulate the system and what they're trying to do. But everything else about relative stability of attractors and critical points is just theory of nonlinear differential equations. I'm sorry.
No,
I'm
I think
2 years old, so please excuse the interruption.
no. I think you're making a great point that because the particular kind of because of the control goal that I chose was attractor switching, that like these things are sort of like intertwined. Like I am navigating around this like critical point to get to my other solution.
Control is fine, but whenever you interject the word optimal, you have to define what your concept of optimal is, because nobody else will know what you're talking about.
Right. I guess I did not show what the cost function for the oscillator problem was, but for the active nematic, let's see here. Yeah, I mean, so these were the components that I chose to minimize, right? You know the time and space average, or time and space integrated, total control input, gradient of that control, and then the sort of the norm, the distance away from where I want it to be. And so those could have included other things. I think another typical one to include would be like the dissipation of the system. Maybe minimizing the viscous dissipation to sort of regularize the system in some way.
But of course, cost is in the eye of the beholder. And so every individual has to define what they consider a cost, just like all of living systems do. And, and so this is explicitly writing down everything we consider a cost. And that, that's what makes optimal control so powerful, is you specify, is it the time you want, the shortest time? Is it the least amount of external control? Is it the distance from the final solution? And you give different weights to all those. Just like in everyday life, you have costs and values, and you put different weights on them. But the other point about the controllability and the uniqueness for these nonlinear partial differential equations, there is no general way to find out about whether it's controllable. And so one needs then various kinds of more heuristic approaches. And so this approach that coming out of the nonlinear fluid dynamics community of the exact coherent states is a very, very powerful way. And then that suggests, I mean, this is how NASA is optimizing fuel to get to deep space, how the Webb telescope just got to L2 is using these saddle points in these higher dimensional spaces. And so what we're seeing in this work is that when you run the optimal control on these very complex systems with many coherent states, many of them unstable, is that solution will perturb it in a way to track along those kind of cost-free paths, just like NASA's doing to send satellites out to deep space by going along these invariant manifolds. And so there is a deep connection between the underlying phase space dynamics and the optimal control.
So speaking of parameterized, so here we can see that there's this parameter gamma G, which, I mean, W could have some physical motivation. It seems like gamma G is inherently going to be parameterizing a family of answers, right? Does that change anything important about the output?
Yeah, absolutely. I mean, the gamma G in this case will sort of like set a length scale over which you allow gradients in the control to exist in the solutions, like how smooth do you want the thing to be. The way that I've set this up here is actually like if I don't make W sufficiently high enough, then I won't even get a solution that gets to the other attractor. It just like won't be worth it to sort of like expend the fuel, right, to go to the other thing. And so yeah, I didn't show any of the other kinds of solutions you can get, but yeah, by varying W and varying gamma, you can create much more. If you like really increase W, you'll get much larger control inputs, right? And it'll really try to force the system. It will use less of the native dynamics of the system in getting to the other attractor in some sense, because it's just going to try to like wipe out whatever's there just to like force the system into a new state. The lower the W, the more graceful it will be. It will try to use manifolds that are already there in the system. That's very hand wavy, and you have no reason to believe me that that's the case, but that's at least what we found for the oscillator network.
Okay, and just in terms of interpreting that parameter W, this is not something where you tell the experimentalists, hey, if you set up your experiment with this kind of W, you'll get this kind of thing. It's sort of your strategy for getting to a solution.
Yeah, 100%. I mean, it's you can definitely make modifications to the cost function to reflect experimental realities, right? Like this is kind of, I chose this cost function because it's all quadratic and nice to work with, right? But really, yeah, its job is just to help produce solutions. And you're absolutely right that like by swooping through these parameters, you're going to end up with different families of solutions. It's just I think that's the right way to think about it. It's just a way of identifying what's possible, right? But it's not like locked to some reality necessarily, unless you really have a exact dollar amount for the amount of fuel or like
but it's all physically motivated. It's like you don't have an infinite amount of light. You shine light on these motors, you're not going to get an infinite amount of stress, so it minimizes how much extra activity you have to put in, and you're not going to get gradients over a micron. Things are going to diffuse and stuff, so it penalizes things that are too sharp. And so it is totally I mean, this is designed so that we can now do experiments, So it puts in everything that we know to the best of our knowledge about optogenetics, is put into this model. So this is a very pragmatic, this is the most pragmatic solution we could think of. This is actually guiding, we're building digital light projectors right now in the lab to do this experiment. So this is all designed to guide our engineering, So, we have so many pixels that we can project in so many seconds, And so, I mean, so in some sense, this is as practical as you can get.
Mhm.
But yeah, there's an infinite number of costs you could put in. We picked the ones that would guide present day experiments.
Oh, that sounds exciting. All right, is there one last question before we transition over to the grad student portion?
I'll ask another question if there's none. You mentioned in the middle of the talk that the targets that the target state is not fixed; it's dynamic, right? It's like some sort of resembles like a limit cycle. So, are you actually explicitly saying this high-dimensional limit cycle is my target, or are you saying like I just want this thing to go counterclockwise, or how do you encode that in the control?
Yeah, we just did it totally literally, and it was just a penalty on Q, so just the director field configuration. We didn't apply a penalty to the flow field, and so we just had this basically it's like a lookup table. Like we knew we had a full period of the precession.
Okay.
And we just sort of interpolated as time went on to yeah. So explicitly written in there. I played around with things like just the circulation, but it ended up being a little bit weird. And I think the reason for that is because in the Stokes regime, you may be able to instantaneously satisfy a flow that does have the attributes you want, but without rearranging Q, just because we're overdamped. I'm kind of shooting from the hip there. I'm not totally sure why, but it was not as robust in producing control solutions. So I just went for the completely explicit form.
Okay, got it. And then one really quick last thing. Is there an extension of this to discrete dynamical systems, or is this totally rely on like continuity and differentiability of your dynamical system?
No, I think you should be able to do this for discrete time. In fact, some of the implementations, some of the algorithms for solving this, for at least for the ODE side of the system, are written as discrete problems. So I think there's no issue there.
Just discrete time and space.
Yeah, I think that should be. I think that should be fine. I guess one point to add that I haven't looked into a lot, but I know is sort of like lingering, and maybe this is something that John has come across or has something to add on. But you can either discretize your system first and then develop the adjoint equations, or you can adjoint first and then develop your discretized equations. And I think there's some debate in the literature over like which of those is better for certain situations. So I guess that's something to keep in mind. But as a general rule, I don't think there's any limitation there for discrete or continuous in space and time.
Okay, thanks.
Yeah.
All right. Well, let's thank Mike Norton again, and we'll end the recording there.